How do you analyze and find the transient response of an RLC circuit, including mutual coupling? Here is an example. In this example, we not only have an RLC circuit in a transient situation, but also we have one active element, which is this current-dependent voltage source. So in this example, this switch has been in position A for a long time, which allows for 24 volt, 3 ohm, and this inductor to reach a steady state. Then at time t0, switch moves from A to B instantaneously. And after that, the active portion of circuit that matters to us would be just a loaded inductor and this resistor of 5 ohm, this current dependent voltage source and capacitor, and then this 20 ohm. We want to construct the S-domain circuit after time t equal to 0, meaning that after the switch changes the position. And after constructing the S-domain, then we want to do the transient analysis and figure out the output voltage in S-domain and also correspondingly in time domain. Okay, so before getting to S-domain circuit construction, before time t equal to 0, this switch has been in position A for a long time. This voltage source, this 3 ohm, and this inductor, all of them, the whole circuit in that case, has reached a steady state. Because inductor is an ideal inductor, meaning that there is no resistor, internal resistor involved. So when it reaches a steady state, the voltage drop across this whole inductor is 0. Therefore, we can just say that all the 24 volt going this way through the inductor and coming back just drops across 3 ohm, and therefore for t less than 0, we can say the current of inductor, which is shown this way, is just simply 24 volt divided by 3 ohm, which is 8 amp. Okay, so we have this information. Now, at time t equal to 0, switch changes the position from A to B. And circuit becomes simply this circuit. So we have an equivalent inductor, Ls. We have to calculate L. This is the position B. And then we have the 5 ohm resistor, and this is the voltage of interest, VO or Vout. We have the current dependent voltage source, 25 Ix. After that we have the capacitor, which is just 0.1 farad, and we have the current Ix going to resistor 20 ohm. Okay. Of course, we are missing one element here, one component here, and that is this is a so-called loaded inductor, meaning that right before the switch changing the position, there is an 8 amp current going this way through this inductor. And because inductor really tries to keep its current not changing instantaneously, therefore at time t equal to 0 positive, right after the closure of changing the position of the switch, there is a current still flowing through the inductor from bottom to top, same direction as before, and its value is just that current is 8 starting from time 0. So in Laplace transform it would be 8 over s. So basically what we are saying is this current that we just computed here, I of the inductor at time positive 0 should be I of the inductor at time right before 0 should be 8 amp. And then since we are saying, okay, effectively we are modeling this current at time after 0 in the form of 8 ut, therefore we are saying its Laplace domain representation is 8 over s, which is shown over here. So this is our S-domain circuit for time greater than 0. Okay, now we have to find S-domain representation of the Vout. So I of x is flowing through 20 ohm, therefore the voltage drop across 20 ohm would be 20 I of x. That's the voltage drop. Now this is 20 I of x, Ix, and 25 Ix, adding these two voltage together. So we get the voltage at this node. Let's refer to it as V1. Actually, it's Vout. This is our reference. So this is our Vout. So Vout is simply 25 Ix plus 20 times this current flowing through this resistor. So we get Vout is just 45 Ix. Okay, let's name this relationship or equation 1. Okay, since we now Vout is 45 Ix, we can calculate the current going through this 5 ohm resistor. So let's name this as I2. So I can say I2 is simply Vout, which is the voltage across this 5 ohm resistor, divided by 5. So we're talking about from equation 1, 45 Ix divided by 5, we get I2 is 9 Ix. Great. Okay. So now I just need to also calculate the current that is coming this way, and for that I need this current that is going through the capacitor. I have the voltage across capacitor, which is 20 times Ix. So I can say, also we know voltage across capacitor is 20 times Ix. Hence, the current of capacitor, which is this current, is just voltage divided by impedance of capacitor. So in S-domain representation, so that would be 20 Ix divided by 1 over Cs. So we're talking about 20 Cs Ix. Therefore, voltage of capacitor in S-domain, therefore the current of capacitor in S-domain is just 20 times C is 0.1 farad, so it's just 2 S Ix. Okay, great. So this current is 2S Ix, this current is Ix, therefore this current, which we refer to it as, let's say, I1, so I1 is just Ix plus Ic. So I1 is just 2s plus 1 times Ix. Okay, 2. Also, let's not forget about this one, which I refer to it as, let's name this 3, let's name this 2. So now I can say, okay, I1 is this in 3, and I2 is this one. So I can find out this current if I want. But what I can do is I can write a KCL for this node, so, or this node, doesn't matter. So KCL or current Kirchhoff's current law at Vout is basically saying the current coming in, which is 8 over S, should be equal to the sum of all current going out. So it would be IL plus I2 plus I1. Okay, so 8 over S is IL. Well, we know the voltage Vout from 1, so Vout, that is the voltage across our equivalent inductor. So V out over LS, that's the impedance of the inductor, plus I2. I2 is from equation 2, 9Ix, plus I1 from equation 3. So from equation 2 and 3, I1 is also 2s plus 1 Ix. Okay, and now I can use equation 1 to replace V out. So maybe I can just write it here. This guy is 45 Ix from equation 1. So I can clean up. 8 over S is equal to, and L, we have to find it out, so is 45 LS plus 2S plus 10 times Ix. Great. So now we have a simple equation that allows us to find Ix. And then let's not forget that Ix is related to V out via equation 1. So what I can do is I can say, okay, V out from equation 1, let's say this guy is equation 4. So V out is simply 9 Ix, and then from equation 4, V out, 45 Ix. And then V out is just 45 times 8. Okay, and then we have 45 times S divided by 45 L plus 10S plus 2S squared. So that is our V out. Equation 5. Okay. Now this L, we need to find the equivalent inductance for this very large inductor. Okay, the nice thing is we just need to follow the current. So this current is going into this inductor this way, and it continues, and then we can see that the current is coming out this way, and the current is going back this way. So when current is going from right to left on top of this bar, then the magnetic field it creates would be toward inside this iron bar, and then for the other one is the other way. So these two, L2 and L3, are counteracting each other, so the effect of mutual inductance between them, M23, would be negative. And you can see that for between L2 and L1, current is going from left to right above, and then after passing below this, going again from the below to the top the other way. So you can see that L1 and L2 are counteracting each other, so the effect of mutual coupling would be a negative one. And contrary to these two cases for M13, you can see that L1 and L3 are helping each other, because for both of them, the way that the current is flowing through the wire around the bar is the same for both, around the core. So that's why for L, we can just say the equivalent total inductance would be the sum of the three inductance, just from the physics of mutual inductance, minus 2 times M12, because these two are counteracting each other, minus 2 times M23, because L2 and L3 are counteracting each other, and plus 2 times M13, because L1 and L3, they are creating magnetic field in the same direction. So it would be plus 2M13. Now if you use these values given and just replace and just put in place in this equation, you get L equal to 5.625 Henry. And then we can then put this and replace L with this number in the equation 5, and from there we can see just V out is simply is simply 45 times 8 is will be 180 divided by S2 plus 5S plus 4. Okay, so this is our equation 6, and from here it's very easy to see what is V out of S, which is just simply 60 over S plus would be 60 over S plus 1 plus minus 60 over S plus 4. And from here we can see that V out of time domain equivalent of V out is just simply 60 times e to the minus t minus e to the minus 4t ut, just simply because we know that the time domain equivalent of 1 over s plus 1 is e to the minus tut, and time domain representation of 1 over s plus 4 is e to the minus 4tut. And this is in line with our expectation, because at time t equal to 0, you can see that it becomes 1 minus 1, so V out at time 0 should be 0. And that is exactly what we expect, because V out is the voltage across the inductor, which we expect that at transition time should be 0. And then at time infinity, the whole current is consumed, the whole energy, magnetic energy that was reserved, saved inside the inductor, is already wasted through the circuit. Through thermal dissipation. So that's why we expect that at time infinity the voltage has to be also equal to 0, which you can see that at infinity these two components become 0, so voltage becomes 0. Thank you.